Hey, hello everybody. So while in the preambles to this, we were talking with Doug that the co-localization as we classically know it isn't actually co-localization. Is what we're doing there is we're comparing intensities between two different channels, regardless of where the things are, and the decision that two things are co-localized is, as we will see on Thursday, is to be taken with a grain of salt. So the actual real co-localization is what Doug is going to present, the object-based co-localization next week. So yeah, without further ado, let me switch to my ZEN screen and show you the tool as, oh, hold on. Do I have to click anything here to share the screen? Yes, here, share screen. There it is. Then share. So you should be seeing this.
Yep, looks good.
Yep. Bunch of dots. So just to start, what have I done here, and what is this co-localization tool going to be? So if I switch off, if I have only a red channel where I have all the high intensity red objects on the top and all the low intensity red dots on the bottom, you can see that there is a very low intensity red object down here that is invisible using the normal grayscales here. And I also have green objects where they are organized on the vertical columns. So on the right side, we have very bright green objects, and on the left side, we have very dim green objects. And again, here, we do have that hidden little dim yet visible green object here on the top left corner. If I turn on both channels, we get a combination of green and red. And we have a red-only object here on the top left corner, a green-only object on the bottom right corner, a green and red object here on the top corner, and a dim green-red object down here on the lower right corner. The idea now is, and that has been, I don't know when this was developed, some 40 years ago, 30 years ago, is the idea of finding out which objects are both green and red and call that co-localization. So the idea here is to take all the pixels and organize them in a histogram, and the button to press is here on the left side. You have this, I don't know if you can see it, if it's zoomed in enough, I can increase the size a little bit. You have here a button that is called, or a tab that is called Co-Loc. And once you press that button, a series of graphs will open. And we have here on the left side, what we see here on the left side is not an image. What we see there on the left side is actually, hold on, let me turn this here off. What we see here on the left side is actually a 2D histogram of intensities in various channels. So we have here on the x-axis, we have the intensity in the red channel. And on the y-axis, we have the intensity in the green channel. So an object here, or pixels that are very green but not red will show up over here. Conversely, objects that are very red but not green will be down here. And objects that are both very red and very green are up here, and all kinds of intermediate cases. By the way, just for your information, this fake image was generated using ImageJ by drawing circles of various colors with various grayscale values. And then I added, there is a function in ImageJ called add noise. I added noise to them so that we can see these bubbles a little bit better. If I did not add noise, I would see a single pixel here of that specific color. So now by adding noise, they spread out a little bit and we can see it a little bit better. So, so this is it. And And with this image, I can show you a few of the tools that are available in the ZEN software. So we have another tab down here in the bottom that is called the Co-Localization tab, and here I have various different drawing elements like a rectangle or a circle. I have here a few buttons. One is called a crosshair, the other one is called table. If I click on table, the table will be on or off. Let's switch it off for the time being. If I click on image, I can see the image, or I may choose not to see the image. So the first thing to talk about is this crosshair thing here. The crosshair is placed inside the left image here. You see this number 3 here. This means this is the third quadrant. If I click anywhere on the image, for example here, I will see a quadrant number 2, a quadrant number 3, a quadrant number 1, and a quadrant number no number, a quadrant number 4 in that case. What does this mean? In classic co-localization studies, one would place this crosshair more or less like this, and we will see then later, a few methods how to select this. But what we're doing here is we're saying that all the pixels that are contained in this number 1 quadrant here are the objects that are green only, because they have no intensity in the red, right? They're all low intensity green objects. All these populations that are here on this axis are, sorry, it was the other way around. Those ones are green and those ones are red. And all the other objects here in quadrant number 3 are both green and red. And this is now the first, in a very simplistic kind of analysis, one would say that everything that is here in number 3 is co-localizing. And we will see that there is a little bit of detail to appreciate there. Maybe are they really co-localizing, or what's the deal here? These objects in quadrant number 3, they are both green and red, but they're all over the place. They can be a lot of green and a lot of red and not so green. They can be very green and not so red. They can be both. They're all over the place. Okay, so this is how these quadrants are defined. Here down here, you see that there is there are 4 buttons organized as the quadrants are. This number 1 button here, I can, for example, choose to paint whatever is in that quadrant with a white color. If I press on this, all the objects that correspond, all the pixels that correspond to these clouds here are painted now in the image in white color. I can also do the same thing for those here. I will paint those in this cyan color. Those would be those pixels. The population there at 0, 0 are all the dark pixels. If I paint them in, for example, in red, all the background will be painted in red. This is usually omitted. People generally don't care about things you don't see and cannot quantify. Things that are not fluorescent are not available in a fluorescent image. So why analyze things I cannot see? I would need a crystal ball to do that. So this can be easily omitted there. However, it is useful to see the distribution of dark values anyway. It tells you something about, has the image been offset or things of that nature. Okay, so the interesting population here would be the co-localizing ones. I can remove the colors and I will see, okay, maybe I can paint this in a canonical co-localization color, which would be yellow. Okay, so this is how this quadrant thing works, and this is how these region buttons work. I can also cut out these pieces of image here by pressing this cut mask button. When I press this cut mask button, a new image is generated where only the region number 3, only the objects that are in the region number 3 are cut out. So there are no more of the other objects. So this can be interesting if you're trying to extract features, the one neuron that is co-localizing from the entire brain of the fish or something like that. You can use that to extract 2 channels that are of a certain amount of colors between them. It doesn't have to necessarily be a green-red image. It can also be time sequences. For example, if you're trying to remove or to keep only the immobile objects, the immobile objects will not change from channel to channel. You could separate them out using this tool as well. Okay, so going back to the, where was it? One of these. Was it this one? No, these were different attempts. Okay, we were here. Load and save refers to loading and saving here certain threshold settings. These threshold settings are the boundaries here of the cutoff for what is below that value is counted as not green. What is below this value here is counted as not red. And in that way, I can choose these quadrants and these things. So there is, however, another type of analysis that can be done. I could, for example, select here a square and select here on the image this particular object here and infer from there, well, what is the distribution of red and green in this object, in that object, or in these two objects, and I can use that to ask the question. So in this object with this specific color here of green and red, let me remove these markings here. So how green and how red is it? This one and this one and that one. And I can find that each one of these blobs exists in a different position in the scatter diagram over here. Okay, and I can draw different types of shape, and I can add and delete and make the lines thicker and change the color of those lines. This is obvious stuff, but now we have explained all the buttons there are in this co-localization thing. There is another interesting thing here in this co-localization tool, which is this table down here. The table down here, forgive me, but I cannot make this larger. I can increase the size of graphics and everything, but it will not increase the font size of the table. So buttons become larger and smaller, but not the table. So I'll leave it at some size like here. And this table is organized as follows. It has here in the first column, it has a scatter region 1, 2, 3, which is the scatter region 1, 2, and 3. And then it has how many pixels are, so it's a superposition of the crosshair on the left and this object here. If I select, for example, this here, you can see that here in region number 2, we have now 7,483 pixels inside that box. And inside that region number 2, so not the black ones, it counts how many pixels are green. And what is the relative area of that relative to the selection box there? That's 29.5%. If I increase this thing, the area becomes smaller. And you see here now I'm starting to populate different. Wait, if I do it like here, I will have now objects in all the different quadrants. Yeah, because the circles are all the same size. All the number of pixels will be similar, 7,860. The relative area relative to that box. Then it calculates what is the mean intensity of channel 1 in that quadrant. It's 60. And the mean intensity of channel 2 in that quadrant is 3.7. Yeah, here there is a little bit of noise. Remember, I added noise, so the value here is not 0. It calculates the standard deviation for both channels. And then here it adds a number of correlation coefficients. The correlation coefficients are only calculated for this region number 3, because that's where the correlation is canonically measured. Yeah. And here you can see the co-localization coefficient is 1.00, meaning that every pixel that is red is also green to some extent. Co-localization coefficient channel 2 is all the channels that are red are also green. It can be, this can distinguish two cases where we have numerous green objects and some of them are also red. So I would have objects, all objects are green, but not all of them are red. Conversely, I can have the case where I have all objects are red and some of them are green. In this case, all of them are everything. Weighted co-localization coefficient and weighted co-localization coefficient is weighted with its intensity. In this case, because it's an artificial case, we will see the weight is 1. And then we have here an overlap coefficient, which is, again, a measure of how many pixels are green and red simultaneously. And here we have a correlation coefficient and the correlation square coefficient. In these two cases, it's 0, because what the software is doing is it's doing a linear regression through these clouds here. It's taking, and we will see that on Thursday, what this linear regression is. But in this case, it's easy to see that the linear regression could be any curve around in here. So there is not a good correlation. So in a situation like this, even though the particles are both green and red, they do not correlate. Meaning, when something turns brighter in the green, it does not follow automatically that it turns also brighter in red. If I select, let me remove that area here. If I selected a different area, for example, if I try to force a correlation to be more perfect by selecting only the ones that are along this diagonal here, you will see here the correlation coefficient goes up to almost 1, meaning that the linear regression through these clouds here is a very precise curve of slope 1, meaning that when green increases, red increases linearly with it. Let me show you a couple of scenarios where this might be intuitive or counterintuitive. We have here, where is this? Is it this one? Yeah. We have here a case where we have yellowish objects, we have red objects, and we have green objects. If you do a simple co-localization by eye, you would say, yeah, well, okay, these yellow objects are correlating, and this is the green population, and this is the red population. If we draw here the co-localization scheme of that, see here, it goes with the display. We see that these two are actually anti-correlated. Yeah, if a diagonal is in this direction, it means that as the green color decreases, the red color increases. They are mutually exclusive, or other way around. As the green color decreases, the red color increases here. So if you are looking at cells that express two genes, then one gene, as it gets more and more expressed, the other one gets less and less expressed. Maybe one is down-regulating the other one. So what we're looking for here is not are two things together across, in a specific cell, but what is the trend of this curve? We have, of course, also here an artificial converse case where we have similarly yellow objects and red and green objects. And if we take a look here at the correlogram, we see objects that are very green, objects that are very red, and some objects that fall directly on the diagonal. So these objects that are on the diagonal are the ones that are expressing the green object of interest, the green protein, for example, and the red protein, and they are going hand in hand together, saying that the production of the red signal depends on the production of the green signal. They are directly linked in this positive way, and this is also something that can be read out here. Perhaps here an interesting tool to demonstrate as well is we saw before that we can select a population here on the left side and figure out, okay, what are those cells, where do they belong? But we can also do the other way around. If I delete this object from here, we can also look at the full correlogram, remove that crosshair. Yeah. And then, oh wait, maybe we can put just to remove the background. You can see here the little red dot, which gives you the threshold. But we can also click inside the histogram here on the left side. I think yellow is not a very fortunate color here. Yeah? But we can also ask the question, hey, these pixels that belong to this population, where are they on the image? And you can see here, those are those. Yeah? If I go down here, those are the other ones. Yeah, here's the thresholds are bad again. Yeah, those are the dimmer red ones, those are the brighter red ones, those are the dimmer green ones, those are the brighter green ones. And down here, this is all background. Yeah, we can also, hold on, we can also go back to this first example here and ask the question. So remember this, there was this other object down here. Right, you can almost see it here, like that. Yeah, that this little cloud here, the red part of the cloud down there, maybe I can increase this. It's difficult to see here, but that red part of the cloud down here is the real background, and that part over here is actually that very dim object that we saw over here. If I have different objects marked here, I have remove this thing so that you can see it. If we have this diagonal marking here, this will be the image region number 111 and the quadrants 1, 2, 3. So it's going to do the correlation over there. This box here is the next set of elements in the table, and I can add another one, for example, here for those guys. And similarly here, it is going to do the correlations and everything for the objects, if I select them on the left or on the right side. Okay. So that is the co-localization 101, the tools inside ZEN explained. More details will follow on Thursday, is like, what does all of this actually mean? In the meantime, if you are really interested, you can always pick up the question mark here on the top right and drag it down, for example, here onto the Co-Localization tab and click it. Then it will have here, wait, if we put here co-localization, it actually gives the help, and there is also a little bit of information is how is the scatter diagram generated. Everything I explained today is also explained here in the help file, and it also has the explanation of what the coefficients are and the literature where this can be found. Yeah, this is the definition of the correlation coefficient, the Pearson's correlation coefficient. And let me go back one. And there is also here the coefficient after Manders. Is after this piece of literature, the Manders coefficient, which is this one, which is another parameter that quantifies colocalization in image pairs. Okay, so all the help is there, all the explanations are there. More details will follow on Thursday. And now I think the best thing is to, open up your microphones and let's start taking questions. Over to you, Doug.
That was good, Chris. I actually didn't realize a lot of the stuff that you could do. I like how you can highlight specific areas in your image, and then I can show that on the histogram or vice versa. It's pretty useful.
Yeah, it can be used also outside of correlating green and red channels. It can be, like I said before, used to correlate anything. You take a static image and compare a moving image with it and say, okay, what are the objects that stay in common between the two images? They will show up as a pixel on the top on quadrant 3, whereas things that move, they will not be in successive frames. They will be in either channel 1 or channel 2. Or noise analysis, if you take the image and another image, then the correlation will be, of course, perfect, but the spread, the cloud, how much it spreads from the diagonal will tell you how much noise your detector has. There are several useful ways to abuse the co-localization tab that go outside of the co-localization and more aptly, you know, the co-intensification.
Exactly. Cool. Did anybody else have any questions?